Hi, this is Scott Vaughn. In this video, we'll look at some Calc 2 topics. We'll look at the convergence of infinite series, the definition, and what that really means. We'll look at conditional and absolute convergence and the distinction between those two, and then try to finish off with just some general applications of why we have to work so hard to understand infinite series. What's the purpose here? So I'll start off with this definition from our book, from the Stewart book. This is the formal definition for the when an infinite series converges. What does that mean? Right? So it says, given a series from n equal 1 to infinity of some sequence a sub n that's equal to these infinite series of terms added together, a1 plus a2 plus a3 plus on and on and on, we will define s sub n as the nth partial sum. So that means the sum of the first n terms. You see, s sub n is a finite sum with this index I up to this subscript n, this value n that is a finite number. So there are n terms here added together, a1 plus a2 plus a3 plus a4, all the way up to whatever n is, a finite number, n terms. That's s sub n. It's called the nth partial sum. It's the sum of the first n terms. So that's a definition. And then we say, if the sequence s sub n. So if you look at s1, that's just the first term. s2, that's the first two terms. s3, that's the sum of the first three terms. s4, the sum of the first four terms, and so on. So that is a sequence that's on top of the a sub n sequence, right? This is a sequence of partial sums. That's what this represents. The sum of the first term, the sum of the first two terms, the sum of the first three terms. Each of those is a different value. Right? If that sequence is convergent, and what that means is that the s sub n's are getting closer and closer to some value s. So in the sequence s sub n, as n goes to infinity, if that sequence of partial sums is getting closer and closer to some value s, if that limit exists and is equal to some number s, that is some real number, then we say that that infinite series, a sub n, is convergent. And we say that adding all these numbers forever, a1, a2, a3, it is by definition the value s. This is restated another kind of more concise way. Infinite sum of terms equal to the value s. So s is called the sum of the series, and if that sequence of partial sums is divergent, just meaning it doesn't get closer and closer to a value, it might be that the sequence is getting closer to infinity, or it just may be that it's oscillating up and down between two values, or it just isn't settling on any particular value. Well, if that sequence is divergent, in other words, the limit of the s sub n's doesn't exist, then the series is called divergent. Well, okay, so how about an example? Let's take a classic one that's often used as a first example. Let's take the sum n equal 1 to infinity, 1 over 2 to the n. So this is a series because of the sigma, and it's 1/2 plus is when I plug in a 1, I get 1 over 2, and then when I plug in n equal 2, I get 1 over 2 squared, and then when you plug in 3, that's 1 over 2 cubed. And so you have this infinite series that is 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and it goes on forever. And we're going to talk about whether or not it makes any sense to add up all these numbers forever. And in fact, what happens here is that we have a definition for how we can make sense of this infinite sum. We will define it. It's a definition. That's really an important point. That it's a definition as to when this takes on a value, and how it's possible that some infinite series take on a value and some don't. Well, some of these really basic, important concepts at the very beginning, maybe I'll take a few minutes to talk through some of those. So we need to distinguish between sequences and series, and a sequence here would be based on this nth term. So this would be like, you could call this the nth term of a sequence. Right? And a sequence is just some function based on whose domain is natural numbers. So here the domain is 1, 2, 3, 4, 5, and on. And this is a formula just like any function, but it's just written in this notation because its domain is natural numbers. And then actually, if you see it like written like this is the sequence. Now, it's pretty clear, I think, that if you look at the limit of the sequence of terms, the limit as n goes to infinity of the nth term, well, the top is constant 1, the bottom gets bigger and bigger. This is a determinate form. It's something that we can just use as a kind of a given. It's already established that this is 0. And so the sequence, I think there's a lot of confusion between the distinction between a sequence and a series in this kind of analysis here. So the sequence of terms is approaching 0, but you're about to see that this series is approaching 1. Right? So the infinite series gets closer and closer to 1, while the sequence of terms themselves are going to 0. In this case, in order now to really make sense of the idea of a series, what we do is we say Sn is the nth partial sum, which is the sum of the first n terms of any particular series, generally an infinite series, right? So in this example, well, we could look at individual partial sums, like the first partial sum. The first partial sum is just the first term of the series, and the second partial sum is the sum of the first 2 terms. S3 is the sum of the first 3 terms. This is supposed to be a plus. S3 is the sum of the first 3 terms. Now, what's happening is that we're actually developing a sequence of partial sums. Right? So this is, if you take 1/2 plus 1/4, you get 3/4. And if you add these guys, you're going to get 7/8. If you add the first 4 terms, so S4, this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. What happens when you add all these guys? You get 15/16, and so it's what's becoming apparent here. And I did this in another video, so I won't go through the whole entire algebra, but it's really a beautiful, fascinating, and neat little derivation. I can actually come up with a formula for the nth partial sum for this particular series. This is generally not possible. It's just in particular special cases when it's even possible to do this. This is what we're looking at here is actually an example of a geometric series, and it's in the case that you have a geometric series that you can actually come up with a formula for the nth partial sum. And those telescoping series, that's where you can do that. So in this case, what happens is it's actually 2 to the n on the bottom and 2 to the n minus 1 on the top. That is actually a whole bunch of, it's maybe apparent, it sort of looks like, oh yeah, that makes sense, but you can actually prove logically that this is actually the formula for the nth partial sum. And that actually takes some work by itself. I did it in a different video, I won't repeat it here, because what I want to say is that we have for this infinite series, this is the nth partial sum. To be able to develop that is a kind of a special case where that's possible. But so that's why this is such an important kind of first example, because we can actually do this, and you can see the pattern developing. This is the nth partial sum, and so it can really illustrate the basic idea of what convergence for an infinite series is about. See, if you look at, that's the nth partial sum, the sequence. You see how I can now imagine a sequence of partial sums, right? We had 1/2, and then we had 3/4, and then we had 7/8, 15/16. You can see where this is going, right? It's getting closer and closer to, well, it's getting closer and closer to 1, right? The nth partial sum in this particular series is written this way, which I can simplify in order to, or rewrite in order to evaluate the limit. I'll write it this way. I'll write it this way because this way it's a determinate form. Here, the top is getting closer to infinity, the bottom also getting closer to infinity. The top gets bigger and the bottom gets bigger, and it's not, as well, if you write it this way, you can make a deductive conclusion based on something already established, which is that this is a determinate form, and so this is going to go to 0 because the bottom grows, so the whole thing is approaching 1, right? It's pretty obvious. So you look at that and say, oh yeah, it seems to be getting closer and closer to 1. That is in fact the case. And so what's happened is this infinite series, because it has this partial sum, it's equal to the limit of the sequence of partial sums. And that's the limit of this nth partial sum, which we know is 1. So actually, this equality holds when this limit exists. Because that limit exists, and in this case it's equal to 1, that's the infinite series. In other words, 1/2 plus 1/4 plus 1/8 plus 1/16 on forever. The reason why we say this is equal to 1 is because we've evaluated the sequence of partial sums. If you take the first partial sum, you get 1/2. Take the first two and you get 3/4. Put these three together and you get 7/8. And put these four together and you get 15/16. And you can now imagine that taking larger and larger partial sums, the more partial sums you can combine, the closer you are getting to 1. And you can see that has sort of been really laid out explicitly here, that the limit of the sequence of partial sums is 1. That's why this infinite series is equal to 1. That's what it means for an infinite series to converge. It's always because the sequence of partial sums converges. Although often, when you go through all these convergence tests, you just can't get a formula for the nth partial sum. That's just impossible to do. So we have to look at all these other convergence tests as ways of determining whether, in fact, the sequence of partial sums does converge. We can't do it based on the actual formula for the nth partial sum. We have to do it some other way, with some other test for convergence. All right, one more really fundamental example of an infinite series, just to kind of make this point about just generally what it really means. Talk about convergence. Let's take a look at this guy again. 1/n, n equal 1 to infinity. So this is the series 1 plus 1/2 plus 1/3 and 1/4, on and on. Does this add up to anything? Well, it gets really difficult to look at the sequence of partial sums in the same way that I did before. But there's a really brilliant idea, which is to look at a sequence within the sequence of partial sums. And that sequence will be, let's look at every time you double the number of terms. So let's look at like the first two terms. The sum of the first two terms is 1 plus 1/2. Let's look at the first 4. This is 1 plus 1/2, 1/3, and 1/4. And here's where the brilliant idea comes in. The brilliant idea that I always mess up. This will actually be bigger than if I say 1 plus 1/2 plus 1/4 and 1/4. Okay, so here I have 1 plus 1/2, and then put those together, that's another 1/2. I'm going to simplify that to say, well, this is let's write it this way. It's 1 plus 2/2. I'll write it that way because this develops a nice pattern. So now I'm going to jump all the way to the sum of the first 8 terms. And then this really clever logic is to say, well, this amount that I have here is still larger than, and I'm going to set this to, I'll say 1 plus the 1/2 that I have here, and then these guys, I'll make them both fourths. I'll change them to both fourths because that makes a 1/2, and then these 4, I'll set them to that denominator 8, right? Because 1/8 is smaller than a 5th, and 1/8 is smaller than a 6th, and so I will do 1/8 4 times. And what do we have here? 1 plus, this is a 1/2, this is a 1/2, this is another 1/2 because there's 4 8s, so 1/2, 2/2, 3/2. So I'm not actually adding all this together because getting a common denominator is just getting worse and worse and worse. But it's just really, really neat to think, okay, well, you can change it to something smaller that makes it easy to get a common denominator here and group these in halves, right? 1/2, 2/2, 3/2. So this is larger than that number. Let's do just one more. If I say the sum of the first 16 terms, and now I won't write them all out because that will get kind of exhausting, we'll go all the way up to 1/16. And that will be bigger than, and if you think through the pattern that I'm going to follow here, I'm going to say 1 plus a half. That's the 1 and that's the half. And then I'll do the 1/3 and the 1/4. I'll switch them both to fourths. And then for the 1/5 through the 1/8, I will say just change them all to 1/8. So here I've kind of rewritten it because I want to. It just seems too exhausting. I didn't skip that much, but maybe I can make the argument now. So this is the sum of the first 16 terms. So here they are. Add it all up to the 1/16, and all of that will be larger. So where should I say? This is bigger than what I'm now going to write. So I'll just copy the 1 and the 1/2, and instead of 1/3 and 1/4, I'll just make them both 1/4. And then for these 1/4, 1/5, 6th, 7th, and 8th, that's 4 terms right there. This is smaller. Those 4 terms right there match the 4 terms. Actually, it matches these 4 terms, 5, 6, 7, 8, right? And these guys replace those 2. And then for 9 through 16, how many terms is that? It should be 8. Yeah, the difference between 16 and 9 is actually 7, but I'm counting both beginning and ending, so there's actually 8 terms there, and I'm going to change them all to 1/16, 1/16, because that's actually less than the sum of all these. And how many will I have? 8 of them. And so if you add this up now, you have 1 plus, this is a half, this is another 1/2, this is a 1/2, and this is 1/2. So 1/2, 2/2, 3/2, 4/2. So here's finally with a pattern that I want to explain. This is 2 to the 4. Right? I've just showed that S, the partial sum of the first 16 terms, is actually more than 1 plus 4/2. And so I would say generally, you can add as many terms as you want, and you will always beat any value, always be larger than any value. So we could say that if you just keep doubling the number of terms, you can have something bigger than any number you pick. So by doubling enough times, so 2 to the power n means how many times you double the number of terms, it will be larger than 1 plus n/2. So this means we could choose any number, like let's say any number. Eventually the nth partial sum of the harmonic series will pass any number. For example, let's suppose, say you have 100, right? So if you can add enough terms, we can add enough terms of the harmonic series and we'll pass 100. So what I'm saying here is the partial sums of the harmonic series, they will exceed any value. For example, 100, I could figure out basically what partial sum will exceed 100. When, in other words, how many times do you have to double the number of terms to be larger than 100? Because you can pass any value. I just picked 100 because, why not? So let's make that, we just established this, right? That the nth partial sum will always be larger than this. So I'll just set that value equal to 100 and solve for n. So 1 plus n/2 equal 100 means that n/2 is 99. So n equal 198. That means you have to double 198 times. You have to double the number of terms 198 times. So that's actually 4.017 times 10 to the 59 power. So that's how many terms you need. Actually, this is not the only way to do it, and I think you can actually get this number down a little bit, but this is one logical way to come up with that, that it takes a lot of terms and that it is eventually, like maybe it's not the minimum, but it will certainly exceed 100 with that many terms. If you add that many terms, 4.017 times 10 to the 59 terms, I am sure that the partial sum of that many terms will be larger than 100. So the conclusion, this harmonic series diverges. I got that sort of comparing it to a sequence of partial sums that will always be larger than any value. But let me go back to the sequence a sub n. This sequence converges to 0. So this is, I think, really a confusing point for a lot of people, is that, hold on, so we have a sequence of terms that are converging to 0, but as you add more and more of them, the sequence of partial sums gets bigger and bigger and bigger and diverges. The sequence of partial sums diverges. All right, well, that took longer to get through than I really anticipated as I started this off. But those are such two really fundamental, important examples that couldn't resist getting through those. Another point that I really wanted to make in this video with respect to the concepts of convergence of infinite series is this first principle called the test for divergence. The way to state this is, given some infinite series, if the limit of the sequence of terms is not 0, then the series diverges. And I'll do some examples. Let's say we take, I had this one in the other video, n cubed plus 1, n cubed over n cubed plus 1. And we just ask converge or diverge. Well, the thing is that these questions come up, and we can often answer these without looking at the sequence of partial sums. Think about the sequence of partial sums for this would be really, really complicated, right? So, but fortunately we don't have to. We have all these tests for convergence that don't require looking at sequences of partial sums, because it gets really hard. And this is such an important, this test for divergence, the concept here. So what happens with this one is that we say, well, look at the sequence of terms, the limit as n goes to infinity of the sequence of terms, n cubed over n cubed plus 1, that's equal to 1. So the series diverges. And that's the end of the story. Diverges. Right? But I think there's a lot of ideas that people get confused with the language here. So let me try to say something I hope helps. I'm going to say the sequence of terms in this series actually converges. The sequence of terms converges to 1, right? As n goes to infinity, you're getting closer and closer to 1. And it's because the sequence of terms converges to 1, we know that the sequence of partial sums will diverge. And I know without actually looking at that sequence of partial sums, because that would be very difficult to actually work out what that would be. Imagine getting common denominators, trying to, capture larger and larger finite sums of terms made up of this formula. Well, that'd be just absolutely impossible to manage. But we have this very important principle that if the terms are not going to 0, then the series will diverge. Now we could prove that very precisely and logically and formally. But you can also kind of grasp the idea sort of intuitively. Think about it. If you're adding something together that is getting closer to 1, you're adding something, that the more you add, the more what you are adding is closer to 1. Well, it just doesn't make any sense that as you add more of these, that it would ever add up to a specific value. These values must go to 0 for there to be a chance for it to converge. But this is really a killer. Even if the terms do go to 0, it doesn't mean it'll converge. Right? We just saw that, so I want to make that point also. It's such an important and subtle. This is one of the Calc 2 killers right there. If the terms don't go to 0, it will diverge. If they do go to 0, you don't have a conclusion. what I'm saying is, given an infinite series, if the limit as n goes to infinity of the terms is 0, there's no conclusion. I mean, that's why I worked so hard on those two previous examples. I mean, because they just illustrate that point. Take the infinite series from 1 to infinity of 1 over 2 to the n. 1/2, 1/4, 1/8. This adds up to 1, it converges. Look, the terms go to 0, right? Take this guy, plug in 1, you get 1, plus 1/2, plus 1/3, and 1/4. It's infinite. Diverges. And obviously, as n goes to infinity, 1 over n, that also approaches 0. So in each of these examples, the sequence of terms themselves converge to 0. So if the terms go to 0, that doesn't tell you whether the series will converge or not. That hopefully will be something you can hold on to. I mean, there are people at the end of Calc 2 and the final Calc 2 that they missed that. There are people in the Calc 3 class, they don't get that. So it's a huge point from Calc 2 to be able to recognize that if the terms go to 0, that's not enough by itself to establish convergence or not of a series, of an infinite series. We've got to go through all these different tests depending on the type of series we have, and that's what it's all about. What you can say is that if the terms do not go to 0, you can then think to yourself intuitively, well, I'm adding infinitely many terms, and they are not going to 0. That's enough, logically, to say that the series will diverge. Right? Once again, that's what's called the test for divergence. If the terms don't go to 0, in other words, if the limit doesn't exist, I mean, they don't necessarily have to go to infinity. The terms could just oscillate between plus and minus 1 or any other value, and therefore the limit doesn't exist. The limit of the terms doesn't exist, the series will diverge. If the limit of the terms does exist, if it's like 1, then the series will diverge. Or if it's any other value, it will diverge. If it's any other value, it will diverge. And if it is 0, you can't make a conclusion. Oh, it's tough. Okay, let's move on. Okay, so now let me move to this idea of absolute versus conditional convergence. Talk about that in principle a little bit and do some examples. So from the definition in the Stewart book, generally the definition everywhere, when we say an infinite series is absolutely convergent, what we're talking about is that the series with absolute value on each term is convergent, right? A series, an infinite series, A sub n, is called absolutely convergent if the series of absolute values is convergent. It always sounds to me, like when we use the word absolutely, I always think of it as like, sort of some measure of confidence, like you're absolutely sure that it's convergent, and you can't think of it that way. Of course, that's just silly. What we're talking about is absolutely in the sense of an absolute value. If you put absolute value on every term and it still converges, then it's called absolutely convergent. And then you distinguish that with distinguish that from the idea of conditionally convergent series. And a series is called conditionally convergent if it is convergent but is not absolutely convergent. So always think of the condition, when you say conditionally convergent, it's like the condition here is leave it the way it was, don't put absolute value, because it converges as it was, but with absolute values, it won't converge. That's the way I think of that. And also I like to think about this absolutely versus conditionally as like adjectives. It's describing the way that it converges, the kind of convergence. There's kind of different types of convergence. When you say something converges, it could either be the stronger one, which is absolutely convergent, or a kind of weaker kind of convergence that's called conditionally. And why did it even come up? The reason this question even comes up, the reason it's even sort of something to think about, is that we can begin to discover series that have negative terms. Right? So they might be negative terms because it alternates sign. Or it just might be that there's sometimes negative terms. Doesn't necessarily have to alternate. And so one of the really useful things that we use is that if you can prove that something is absolutely convergent, then it will also be convergent. Um, and then also there's something significant about whether or not it's absolutely versus conditionally convergent in terms of how it affects rearranging the terms. All those I'll get to later. Let's do some examples. Let's take a look at this guy. This guy is actually an alternating series, and it's a geometric series. Because it's a geometric series, you can actually tell exactly what it adds up to. Not only that it converges, but what it converges to. Let's do that for just first. Right? So this is a geometric series. You can tell the first term, when you plug in 1, is actually negative 1/2. And actually the common ratio is what's in parentheses here, which is also negative 1/2. I could say that it converges since the absolute value of the r is less than 1. And because it's geometric, I know what it converges to. I know that it's equal to the a value over 1 minus the r value. This is the sum of an infinite geometric series. This formula only works for geometric series and when they converge. And in this case, we have a geometric series that converges, and it's actually a negative 1/2 for the a value. And the r is negative 1/2. See how I have to do 1 minus a negative 1/2 there. So this is 1 plus a half is 3/2. All right, so it's adding up to negative 1/3. That's interesting, right? So you have negative 1/2 plus, when I plug in 2, the next term is 1/4. When you plug in 3, plug in 4, plug in 5, adds up to negative 1/3. Interesting, right? I want to just make a note here. I might be wondering about this. It's not only this way that we could write it. We could write it as, well, I could also write it this way. Let's say just if we start with 1, go to infinity, we could put the a value in front, and then we could put the r value here, and do n minus 1. That way, when you plug in 1, you get 0 there. You get negative 1/2 as the first term. You could write it this way, and you could also write it in another way. We could say start at 0, go to infinity, and let's see, what would I want to do? Maybe I could say I want my first term to be negative, so let's make this n plus 1, and then 2. Well, that's another way to write it. This is another way to write it. I can go in all kinds of different things you could do here. I'm not sure why I'm doing all this. I guess I wanted to say something about how, you might recognize it as an alternating series if I wrote it this way. And you might recognize it as a geometric series if I wrote it this way. And they're all the same thing. And what was really the point about all of this? Well, this is a series that if you took absolute value of all the terms, it will still converge. It'll converge to something different. That's generally the case. The only time that it would converge to the same value is if all the terms were positive to begin with, right? So this series, no matter how I wrote it, this is the same thing. If I put absolute value, I get a different series which I know will converge. This is a different series. It's also geometric. It has an r of 1/2 and a first term of 1/2, and it's convergent because the r is less than 1 in absolute value. So because when you take absolute value of every single term, you get another series that actually is convergent, you say that the series is absolutely convergent. Let's compare that one with this series. Well, if we just start off with this series, and I just ask the question, does it converge or diverge? This is a good example for the alternating series test. First thing you check in the alternating series test is, does it alternate? And it does. The next thing you would look at is the absolute value of the terms, and that's 1 over n. And if you look at those terms, they actually don't increase, right? Because they actually decrease. So the n plus 1 term is less than or equal to the n term, so that checks off that the terms actually decrease, because they really decrease. As n gets bigger, you get smaller and smaller for the b sub n. Because it decreases, it doesn't increase. All I need was it doesn't increase. That's the case. And finally, the b sub n's go to 0. That checks off because 1 over n goes to 0 as n gets bigger. So it converges, as it is, like this. And it was the alternating series test that made that conclusion easy. However, if you take absolute value of this guy, absolute value of each term, not absolute value of the whole thing, the absolute value of individual terms, of course, that becomes the harmonic series which diverges. So that's an example of a series that is conditionally convergent. A series is called conditionally convergent if it is convergent, but it isn't absolutely convergent. It's convergent as it was if you left it alone with the alternating sign. In this case, it's an alternating sign. If you leave it as it was, it converges. But if you take absolute value of each term, it becomes a divergent series. That's precisely what we call a conditionally convergent series. I have this picture in my mind about convergence as a kind of conditional and absolute as a kind of adjective. So you have some series that I would say are absolutely convergent. And that's kind of the strongest kind of convergence. And then there's another set that is larger that's conditionally convergent. And then everything else is divergent. There's no such thing as conditionally divergent or absolutely divergent. What happens is that if you look at the set of all series out there, all infinite series, some of them will be absolutely convergent. That's kind of the strongest type of convergence. There is another classification that's a little bit weaker, and I'll talk about what I mean by that. It still technically converges in the sense that you can say that the sequence of partial sums will add up to a number, but it's a kind of a weaker way in which that's happening. So that's a larger group that are conditionally convergent. And if it's not in this group, then it's a divergent series. Let's take a look at these two examples, determine whether they are absolutely or conditionally convergent. So number one. I think what we could do here is just go through looking at this with the alternating series test in number one. What I do is I say, let B sub n be the absolute value of the terms. So first, yes, it alternates. Number two, with the B sub n's equal to this function, each term is less than or equal to the term before, right? Because this is a simple enough scenario when you have a constant number on top and the denominator keeps getting bigger. If the denominator keeps getting bigger, the terms will actually decrease. So this is certainly true. And number three, well, the absolute value of the terms goes to 0. The B sub n approaches 0 because this expression is going to 0 as n gets bigger and bigger. So we can conclude that this series, this alternating series, converges. However, we will now consider the absolute value of the terms. That absolute value will take out that alternating sign, and we have this series. Now, I already did this particular series in another video where I got the fact that it diverges by the integral test, and we could do that again now, but it's maybe another way of showing this diverges might be worth seeing. One thing I want to point out is that you can't say this is a p-series. P-series has to be n to a power p and not n plus 1 to a power p. Now, it's close, I know, because you could just change the index and make it a p-series. But as it is written like this, it's not a p-series. And so you can't make the conclusion that it diverges because it's a p-series with like p equal 1/2. It's not technically a p-series, at least not written this way. So let's go another way to show that this diverges. Let's do a comparison, limit comparison. Yeah, let's do the limit comparison test with a p-series. So, which is a divergent p-series. So the limit as n goes to infinity of the one that I'm given divided by the one that I'm comparing. They're both positive terms, so limit comparison works. It doesn't really matter which one you put on top and the bottom unless you want to use that extra little rule that I use, that if you are comparing with a convergent and you get 0, it still converges, or you're comparing with a divergent and you get infinity and it diverges. If you want to use that rule, then it actually matters that you put your comparison on the bottom. According to the Stewart book, it doesn't really matter as long. So I'm comparing with a divergent series, and as long as I get a number that isn't 0, a finite number that isn't 0, I can make the conclusion that the one that's given will do the same thing as the comparison. Let's see what happens when we evaluate this limit. We'll simplify it. We'll go limit n goes to infinity. Take the bottom and flip, so we get the square root of n on top over the square root of n plus 1. Now the top goes to infinity, the bottom goes to infinity, but we can rewrite this. And at this point, we can go on and on for a while, but I think you can make this logical deduction here. You can say that square root is a continuous function. What's inside gets closer and closer to 1, so the whole thing will get closer and closer to the square root of 1. Yeah, it gets closer and closer to 1. Now, that fact that I got a limit that exists and I compared with a divergent series means that the given series, this guy, will diverge. So the given series in absolute value diverges, right? Which all that means now, finally, conclusion. Because this series, when you put absolute values on each of the terms, it will diverge, means the series is only conditionally convergent. It's convergent if you leave it the way it was with the negatives. Now, going back to the question, there's a kind of point about the order in which you do this work. You could just begin by checking for absolute convergence, and if you get that, you could just be done. Now, if I had done that with number 1, checked for the absolute convergence, it doesn't converge absolutely, but then I'd still have to confirm that it converges as it was, and therefore is conditionally convergent. So it actually kind of makes sense if you want. There's a logical reason why it makes sense to just check for absolute convergence first, because you might actually be done if it actually converges absolutely. You wouldn't then have to go any more work. Like for looking at number 2, I could say, looks like it's going to converge, maybe alternating series, but then I'd also have to check absolute convergence. You know what? I could just check that first. And if it didn't work, I'd still have to go back to check for the, whether it was conditional, whether maybe would converge perhaps with the alternating series test. Let's just do absolute convergence. We could just do that every time. First, that if that seems like a good idea to do, like in number 2 anyway. Let's do that. So looking at number 2, rather than going through alternating series test to see if it converges as it is, I will eventually have to do the absolute value. Let's just do that first. To check for absolute convergence, you take the absolute value of every individual term and look at a new infinite series and check whether it converges. Of course, that changes the infinite series. If it converged to something absolutely, it would converge to something else differently potentially if you took away the absolute value. So in this case, we have 1 to infinity of just 1 over 2n factorial when we take absolute value of individual terms. So we're looking for the convergence of this infinite series. Now that factorial suggests ratio test. So let's go with ratio test. When you do the ratio test, you take a limit as n goes to infinity of the absolute value of the n plus 1 term divided by the n term. In this case, the absolute values don't matter. But what happens here is, this is where I was talking about before in that other video about how everywhere there's an n, you need to replace it with parentheses and an n plus 1. This is an example. So the n plus 1 term is 1 over 2 n plus 1 all factorial. And then the n term is 1 over 2n factorial, like that. Maybe I'll just write it this way. 1 over 2n plus 2 factorial times, and when you flip this fraction, get 2n factorial on the top. 2n plus 2 is bigger than 2n. So this is the one that you start subtracting 1 and then 1 more and then 1 more to look for something to cancel. What happens is you get 2n plus 2, and then 1 less than that is 2n plus 1, and 1 less than that is 2n, and then 1 less than that would be 2n minus 1, but I'm not going to write that because I can see the 2n right there. So it's 2n factorial, and then up here I have 2n factorial, and that's what cancels. I know this is a confusing point that people mess up. If you write 2n factorial like that, I'm going to mark it wrong. That isn't the same thing. This is the factorial of 2n. It's not 2 times n factorial. Those are different. Alright, so if those cancel, this is the limit as n goes to infinity of 1 over 2n plus 2 and 2n plus 1. Of course, that's pretty easy. N gets bigger and bigger. The top is constant, so this whole thing is going to 0. And that 0 is the limit, which is less than 1, which now, because we're doing the ratio test, implies that the series actually converges with absolute values. Right? Since it converges absolutely, anytime any series converges absolutely, it will converge in its original form as well. If that's different, then it would converge to something different. The series that we have here will converge to something different than that one, but we can say that this series converges absolutely because it still converges when you impose that extra condition on it, when you impose that extra sort of extra modification, right, where you put absolute value on every term and it still converges. That's a stronger kind of convergence, the absolute convergence. So this is a series that is absolutely convergent, and I don't have to go back and show that it converges in its original form, because if it converges absolutely, it will converge as it was originally as well. All right, now so there's so much more that's so fascinating to talk about here, but I know this video is going on for a really long time, and I'm going to have to finally get to the end of it, so I'll just have to leave this for another time. But what's important about this idea of conditionally convergent? A series that is conditionally convergent, what's significant about that is it turns out that the order in which the terms are written in the infinite series will affect the infinite sum. So it's still true that the more terms you add, you will get closer and closer to a particular value. But it's a kind of wishy-washy kind of complicated kind of idea where it depends on the order in which you specify those terms. In fact, ultimately, it's proven, you can prove that rearranging the terms of a conditionally convergent series will allow you to come up with any total sum, any infinite sum. You could pick any number, and you can rearrange those terms so that it will add up to that value. So it almost feels like, well, that isn't really, you can look at a conditionally convergent series as adding up to a value, but it could add up to any value you want depending on how you rearrange the terms. So that is a kind of weak convergence in a sense, the way I look at that. And then it's the absolutely convergent, that it doesn't matter what order you put the terms, it will always add up to the same thing. That's a stronger kind of convergence. Rearranging the terms of an absolutely convergent sum does not change the actual sum, right? So it's a stronger kind of convergence that you can sort of be, in some ways, more sure about. You're absolutely sure of what it converges to when it converges absolutely, because it will always be the same value regardless of the order in which the terms are written. So I'll just leave it at that. I think pretty much there's some interesting examples to look at for this, but I think I'll move on to some of the sort of basic applications as to why all these infinite series are significant, and it's one of the examples is dealing with absolutely convergent series and how they are very important and used in the next class that you would typically take after this, which is the differential equations class. So I'll just close out here with some applications of infinite series. Like number one point I want to make is this just sort of fundamental theoretical applications that are directly in mathematics, but that then also have their own applications in many fields in science and engineering. For example, this relationship right here, such a beautiful, fascinating result in and of itself, and it's key to much of the work that we do in the differential equations course, which is then applied through electrical and mechanical engineering to solve problems there. Well, this result, how do we come up with some equality like this? One of the ways to establish this is with doing infinite series for e to the power ix, an infinite series for cosine, an infinite series for sine, actually developing the equality that this infinite series e to a power ix can be expressed as the sum of these two infinite series shows that this is a relationship that's true in the infinite series. So that's one place where infinite series provides these exact perfect theoretical results, which are then have their own applications. And then another place I just want to talk about is how what infinite series provide as a way to find approximations. And a perfect real-life application of that is in finding area under the bell curve. That bell curve, in its most general form, looks like this, but even just simplifying it to a form like this is something in Calc 2 that we will, I hope, at the very end, we can get an antiderivative for this guy with an infinite series. Because up to the point where you study series, there is no way to find an antiderivative for this. It doesn't have an exact antiderivative. The only way to get an antiderivative for this thing is to approximate it with an infinite series. And then you can evaluate it for some interval. And that's one way that we can find the area under the bell curve, is using infinite series to get approximations to the area under the bell curve. So another really important application of infinite series. Okay, that's going to have to be it. Hopefully this has been helpful. Thank you very much for watching, and good luck with Calc 2.